So motion of a stretched string, we want to physically first motivate the model that's called the wave equation, and it's a PDE. And then once we have the PDE, you know, we then want to solve it, you know, the old, no, so question is, so the cutoff for the exam was on Wednesday, so wave equation will not be on the exam, but wave equation will, you know, be in our lives from now on in a fun and exciting way. So yeah, yay. Okay, so yeah, so here's the setup. And so this is the part, you know, we need to rely on your physical intuition and you know, let's see how that goes. So here we have a string that's tied at two ends. Okay, so I'm going to say this is x equals 0. Oh my goodness. And this is x equal capital L. All variables you're familiar with. And, you know, kind of already setting it up, right? So it's tied at the two ends. And so there's some tension here. You know, there's a tension on the string. So, you know, you should think about a guitar, not exactly, but basically a guitar or a violin string that's tied at two ends. And we're assuming, now there's many assumptions now, you know, these are part of our boundary conditions, and we'll get into the technical aspect of it. But for now, we're just assuming the ends are fixed, right? So maybe, you know, they're not moving. I don't know why I just drew two lines. I have no idea. Anyway, so the ends are fixed, they're not moving. And so now imagine we pluck this string, you know, maybe with a guitar pick or your finger, you pull the string up and then you let it go. And then now we're, you know, then it goes up and down, up and down, up and down, right? The string vibrates now. And so there's two pieces here. And so this is the part I want you to get into the PDE of it. Remember, PDEs, we have more than one variable, right? We have space and time. So here, to me, I want you to think about it now. There's two things happening. One, we have this string that's going up and down, and it's a wave in time. You know, what do I mean by that? Like, for example, just fix one point on the string. So just pick a point and in your mind, pluck the string and just track the motion of that single point. That single point will bounce up and down. And if you put on the x-axis time, this single point here will draw a wave in time as it goes, if you just fix that single point. But then there's also this entire string that forms a wave. This actual string, as it goes up and down, is forming a wave. So there's a space wave where here we're considered with the actual shape of the string. So, you know, what's the actual, if you stop time at any moment in your vibrating string, what's the shape of this string? That's one question. And the other question is, if you track an individual point on the string, its journey through time, you know, there you have two different waves happening. Okay, so here we want to, you know, we're going to create this physical model that's a function of x and t. And you'll see that in the actual mathematical solution, you'll see that there's a space and time wave. Okay, so, you know, it's an interesting exercise in how do you think reality works? You know what I mean? So, okay, so here we go. Let's do the physics of it. And as usual, Facebook or Zoom's trying to mess with me. Okay, so consider horizontally stretched string, ends are tied down. The string moves in time, and we wish to track the position of each point on the string. And we also want to know the shape of the string at any point in time. So here's some technical details, you know, to think about if you haven't sat around and thought about how a string moves up and down. I surprisingly have spent a lot of time with this. So here, the position in reality, the position on any point on the string is not entirely vertical. So here, let me just do a little experiment with you. So here, suppose we have our string that's tied down. And here, let me fix it at the ends here. So here we've got the ends are fixed. If you pluck the string, and if we assumed every point moved in the vertical direction, so if you assumed every point on the string moved in a vertical direction, then we wouldn't get a plucked string. Then, I mean, what would then happen physically is the entire string would be up here. But that's not what's happening, right? Here, the ends are fixed. And so here, what we have is that the ends are fixed. And really, there's only one point, a point in the center of the string that moves directly straight up. If every other point moved directly straight up, the entire string would move, it would be parallel to itself. So here, away from the further away you get from the center, there's a little bit of a curve in the motion of the point. Because it's not straight, so it has to curve. And you can either curve left or curve right. And so this is the part where you have to think, do you believe this? In your reality, how does a string behave? Now, if you have some spaghetti hanging around, go ahead and, throw it against the wall, see what happens. Okay, anywho, so yeah, so that's what we've got going on right here. That's what this whole deal's about. So this is the idea that now when you pluck the string, there's a little bit of arc here in the motion. We're tracking a single point. I'm trying to see where's that point going as the string flexes up and down.
Dr. Bach?
Yes, go ahead.
So when you pluck this string with the endpoints fixed, then the string is uniformly deforming. So it's getting thinner, basically, correct?
Yeah.
Okay.
There's some slight stretching happening in this string, and it's basically, from what I understand, and I'm not a physicist, but this is some type of spring.
Right, where the material is being stretched, and that's the internal. Right.
Yeah. It's the tension. Yeah. Go ahead.
So that tension is the same everywhere, correct? Is that the other assumption we're making? Like
yeah. So we're now going to look at the forces of the tension in the horizontal and vertical directions, and say that the tension in the horizontal direction is balancing out. And then in our model, we're essentially going to focus just on the tension in the vertical direction, and we're going to assume that we're plucking the string, but like in all things in calculus, we should think of it as we just plucked it very slightly. It wasn't like we really hit the string hard and it's a big vibration. We just plucked it gently, and it's a very small little delta vibration. And now we're trying to formulate our model in that environment.
Thank you.
Yeah, of course. Evan.
So the tension in the string is just the resistance of the string to deformation when it's plucked and there's waves in the string, right?
Yeah. I mean, I guess it's a function of the material of the string, how the diameter of the string. So there are some certain physical factors here, right?
Okay, because the textbook mentioned that in real life strings have a certain resistance to being bent, but that in our idealized string, we're not considering that. So this resistance to being bent is different than the resistance of the string to being stretched, right?
I guess so. Yeah, the physical part. Yeah, I'm gonna bust out some strings here soon, but yeah, we're training the brain. So one of our assumptions on the next slide will be, we assume that the string is perfectly flexible, which I think is the no resistance thing. So here, the other thing is there is some stretching. So we actually have, so U is the vertical position. I mean, I guess it should really be a function of arc length, because there is some stretching happening here, and this is gravity. This is gravity here. And so these are the forces in our model now that could affect things. And so now we're going to try to, build a model. And as I say, model building to me is an art, people have really good intuition, can do this well, and I want to be one of those people when I grow up one day. Yeah, so, and of course, this is a very famous PDE's model, right? I didn't invent this. So if you have issues with this, don't take it up with me. So with no motion, the string has the density is delta of S, where S is the arc length. And here, this is a mass per volume, okay? So, because you have different types of density. This is not the linear density. We'll get to linear density here in a second. So this is mass per volume. A of S is the cross-sectional area, which in theory does not have to be constant. So these are all possible ways we can, eventually we'll start with a simple model, and then these are all possible ways we can complicate the model. A will be the cross-sectional area of the string. For our simple model, we'll just assume that's constant, that the cross-sectional area is fixed from one end to the other of the string. So U of S is this vertical displacement at the arc length so if you go to halfway along the string and pluck it, what's the vertical displacement there? And the string will stretch a little bit. So I think it technically should be a function of arc length, but we will very soon just replace this with the horizontal distance X for our simplified model. Because the idea here is not to think we've plucked it very hard, but just a very slight, vibration is happening and the string is moving, in kind of a very small delta amount. And we're very close up and looking and seeing what's happening in slow motion, so that we can analyze. So now we can find the linear mass density of the string by taking this density, which is mass per volume, and multiplying by the cross-sectional area, which I'm assuming now is constant. So if you've got your volume and then times your area. And so now you have mass per length is our units, and this is our what we call our linear mass density. Again, we do the one-dimensional model. Of course, this can be made a whole lot more complicated, right? So here, the boundary conditions we can immediately translate when we say the ends of the string are fixed. So that's saying there's no vertical movement at the ends of the string. So, and the vertical, so fixed means the vertical displacement is 0. And at the ends of the string, we're at 0 and L. And, there's just like with our heat equation with the rod, where we've had possible internal sources of heating, here we have some external forces that could affect the vertical position of the string, such as gravity, a violin bow, a guitar pick, depending on whatever you're applying the situation to. So just if there's no external force present and no motion, just starting out, if we just tie the string, the two ends, and do nothing to it, then we have what's called equilibrium, trivial equilibrium, or the equilibrium position. It's just a flat string. And here, the arc length, so now we're going to switch from arc length to X, the horizontal distance along the string. Here, arc length and the distance along the string X are the same. Yeah, Evan, go ahead.
I just had another question about the physical nature of this problem. So I have a string right here, and I'm not applying any attention to it.
Yeah.
So supposedly there should be gravity acting upon the string, and it should be sagging in the middle, but it's not doing that. So I'm wondering what force is resisting the force of gravity, and if this PDE accounts for that force, whatever it is.
I think in the case of the wire you're holding, it's that thick plastic is actually resisting, is providing its own support and resistance to the very thin metal wire that's encased in there,
Okay, so this is that force that's resistant to the bending of the object that the textbook mentions, right?
I guess so, yeah.
So we're not accounting for that with this PDE.
Not at the beginning of this model, no.
Okay, got it.
And I think also, we should imagine the diameter of this string is very small. It's, So I think even that cord you're holding, the diameter is quite large compared to the kind of game we're playing. Think of a very thin guitar string or a violin string, very thin, or hair, even a human hair, So yeah, we assume the constant tensile force, the constant tension along the string. And for a very small vibration, we essentially assume arc length here. It's small enough that we just replace it with X. And so here's the big kind of model assumption that is a starting point that we're ultimately assuming for this string that's tied at two ends. You pluck it just very slightly, and we're trying to track the vertical vibration. There we can assume the vertical position, we can write that as a function of X, the point directly below it. And we're assuming the motion is directly vertical, even though that's not realistic. If the ends are tied, all the points can't be moving vertically up, So here we have, it's a function of X. And now we've brought in time, of course, because we assume these, there's this dynamic behavior in time as the string vibrates up and down. So if you fix time now here, if we fix this variable t, if we let that equal some constant, greater than 0, then that becomes a function of X. And that's the shape. If you graph that with respect to X, that's the shape of the line. And so, once u of xt will be now what we're looking for when we're trying to solve the wave equation. And so ultimately what we want to know is the position, the vertical displacement, the shape of the string, for any point and at any time. So again, we want to know space and time, what's happening in both dimensions. So some more assumptions on the kind of the physical aspect of the string, that we assume the mass of the string is constant in time. It's not pulsating or something like a neuron or, like a nerve or tendril. We assume it's perfectly flexible, has no stiffness, no resistance to bending. So that's interesting. I guess think of a very thin, fine human hair. So, technically speaking, the string is stretching when the actual length of the string, I don't, it stretches a little bit. That's how it can move up and down, I believe. Physically, that's what makes sense to me. And so we say that change in length is a delta L, it's negligible. And the forces are in the tangential direction. So there's no transverse force, no torque. So no torque means it's not twisting. And transverse force means it's not stretching and compressing in the horizontal direction. Because here we've tied the string at two ends and those ends are fixed. Now, there's room here to build up to more complicated models where the ends are moving, right? You could have, so there's a famous one where you have one end is fixed and the other end moves, and you can have it, maybe move up and down or left and right, but those are all, complications to the model to consider for another day, and what would be considered how research is done. You start with a simple model, understand what's going on there, and then make it slightly more complicated. And now you're doing research, figure out what that does, and then make that slightly more complicated, and go in these little measured, baby steps. So here I just I don't know why I repeated all the assumptions again for some unknown reason. So the motion is always perpendicular to the x-axis. So there's no horizontal motion. There's no motion along the x-axis. I don't know, that's redundant. And the vertical motion occurs in a plane. So there's no twisting, i.e. there's no torque. Evan.
I'm sorry, this is my last question about this thing, but
don't be sorry and ask away. This is,
Okay.
I wanna, you know, to me, this is like a probability class where some part of it is not intuitive. So I wanna get there. Yeah, please go ahead.
Okay. So the tension on the string is the resistance of the string to being stretched.
I
So we're
guess so,
assuming that
yeah.
there's tension on the string, but that it's not enough to deform the string, or that it doesn't stretch the string enough to where it significantly affects our position variable, right?
Yeah, I guess so.
Okay.
It's a taut string, so there is tension. And yeah,
But the
but
stretching that this tension gives is negligible, is what we're
yeah,
saying.
it's a delta L, right?
Okay. So
Yeah,
there's tension, but not too much tension, basically.
something like that. It's, you know, because
Okay.
the string itself is so thin and fine, you know, the little tension there's enough to now cause this. You know, these are kind of these idealized environments, you know, when they create these models. So yeah. Yep, let's all, you know, pluck some strings this weekend. Okay, so here we go, folks. We're gonna now start introducing, you know, variables and math and whatnot, and try and create a math world from fake real world, right? We're not even in real world, we're in fake real world. And now we're gonna go from fake real world to math world. Okay, here we go, wave equation. Well, so, and you know, you physics people, you know this better than me. I mean, I have no idea. This is, I like to come in where we have the equation, I'm trying to do the math part. So anywho, I'm gonna do my best here. We're balancing all the forces in the vertical and horizontal direction. And so, and then, you know, using the fact that force equals mass times acceleration. And so we'll balance out the forces, and then, so we'll calculate the mass term. Acceleration will be the second derivative of u with respect to time. So, you know, we're starting to get this PDE. And on the other side, we'll have to also balance out the forces. So, as I said, we assume no motion in the horizontal direction. And so what that means is if capital T represents the magnitude, so the tangential force, I guess, should be a vector. And so here we're looking at the magnitude of that vector. So here T is a scalar that represents the magnitude of the tensile force, which you know should be a vector. So then for some small interval here on the string, x to delta x, okay, we've plucked the string, and I want to see when we've plucked this string, now it's vibrating up and down, what's going on with the tension, the you know, the force is due to the tension. And so here I want to look at, you know, the tension here. I want to break this up into, you know, there's this vertical component and a horizontal component, you know. So now we want to, using the angle here, we can, you know, find mathematical expressions for the vertical and horizontal component of this force due to the tension. So T times cosine of x, that gives us the tension in the horizontal direction. It's just, you know, you can break this into these two little, and then just using trigonometry, you can find the length of these here. So T is like the hypotenuse. So this is like the hypotenuse times cosine is giving you the length of the adjacent side. And so that's the length of the arrow in the horizontal direction at x. And it should be equal to the forces, the tangential forces in the horizontal direction at x plus delta x. And so these forces we're saying cancel each other out. If we multiply here the vertical forces, if we have replace that with sine, that's what we're now really ultimately trying to model, because we've assumed there's no horizontal motion, horizontal stretching. We're only assuming vertical. So that's kind of the direction we're really interested in. And so here we assume that, you know, we did a similar kind of assumption with the heat equation, where we assume in the integral this heat energy is 0 for every little delta x slice, and the only way that's possible is if it's, you know, across the board constant or something like that. So here it's kind of the same idea, that here the horizontal forces are balanced independent of our choice of the x value. And so here the only way that's possible, and it's, you know, is because we're essentially assuming we just have this constant horizontal force. So in the horizontal direction, the tensile force is this fixed T sub 0. I mean, when a string actually flexes, it's more dynamic than that, right? So that may not off the bat be a reasonable model, but here's the art part of building a model. If you try to account for everything that's going on, it's too complicated. You got a, you know, cuckoo clocks happening. There's too many moving pieces. You don't even know where to start to solve the thing, much less be able to formulate it. So it's really being able to understand, you know, really being able to create this artificial kind of cartoon version of what's happening in your mind and converting that into a mathematical formulation. I mean, I do really think this is not easy. Going from this physical model and this idea of a string to now, let's write down some equations that are supposed to accurately describe what's happening in reality. And then let's solve those equations with math and get solutions that are accurate. Of course, we know it seems impossible. Of course, we can do this because we've, you know, and we've done it. Math conquers all. Okay, so here we go. Let's build the model and move towards getting a PDE, because that's what this class is about, solving PDEs. So here we go. We're using this formula, force equals mass times acceleration. And we want to balance the forces in the vertical direction. So here on the left-hand side, I have the forces in the vertical direction. So here, this is mass. So this is the linear density. That's mass per length times the length. So this is mass. The acceleration, so this is our theoretical acceleration of our variable, which, you know, we're trying to find u. If you use the vertical position, the second derivative with respect to time is acceleration, and now I've got force, mass times acceleration. On the other side, and this is now a force. Okay, so now this is a force. On the other side, we calculated this is the magnitude of the tensile force. So there's a vector that's a force, and we've taken its magnitude, and that's this. So that's the magnitude of the force times the sign that gives you the vertical direction. And here they're moving in opposite directions. We kind of think of it as it goes up and down. And so we have forces moving in opposite directions. That's why I have this minus sign here. At delta x, we're assuming it's kind of going down, and at x, we're kind of moving, going up, or vice versa. And so the minus sign is to account for the opposite motion. And then we have external forces, you know, such as gravity. And so here, this is our gravitational force, which is pushing down. So there's this minus sign. And again, rho times delta x is mass, and g is our acceleration due to gravity. So that's your gravitational force. And here are your forces, you know, due to this string going up and down. And in our model, on the other side, in our math, that should equal, you know, if we can accurately capture this function u as a function of x and t, which is the position, then everything we've written on the right-hand side should also equal all of this stuff we've written here on the left-hand side, which is a theoretical calculation of that same, of those same forces using, you know, a function we don't know yet, u. So now I'm just going to do a little bit of, this is basically the wave equation. It doesn't look like a PDE yet. So now we just have to do a little mathematical manipulation and take a limit. And then we'll get, so we've got, you know, a partial derivative on the left-hand side. We want to get a partial derivative on the right-hand side as well. So we just have to do a little bit, some math trickery, and then take a limit, and then we'll have our wave equation, okay? And then, you know, the next order of business will be, you know, how do we solve it? Separation of variables, convergence, that kind of stuff. Okay, so now I'm going to do some math manipulations, okay? So this is nothing other now. We're now just going to try and get partial derivatives on the right-hand side of this equation up here. This equation here will now become the wave equation. Okay, I'll show you how we'll make the right-hand side look like partial derivatives. Okay, so first, we have this assumption that this the tangential force in the horizontal direction was constant. We call that constant t sub 0. And so I can solve for t of xt. This term t of xt, it appears in our equation. So what I want to do is solve, find, you know, I kind of want to replace that. So here we can write t of xt as t sub 0 over cosine xt. And now if you look in our equation, the t of xt is being multiplied by a sine term. So let me go ahead and multiply in there a sine term. And so I'm multiplying a sine to both sides here. T times sine. On this side, you get sine over cosine. So there'll be a sine right here. A sine right here and a sine right here. So this is the term right here, t times sine. And on the other side, I have t sub 0. Then sine over cosine is tangent. So you all took calculus, right? Calc 1. Remember how we talked about the derivative is the slope of the tangent line? This tangent right here, that's going to turn into a derivative. So now we're going to replace these terms. Basically, now we've shown this. We have this identity now. And I can replace this term as well as this term here using this equation. And so that's what happens down here. We have that term got replaced and this term here is replaced. Everything else is the same. So now, look, there's this delta x right here. I've got a delta x right here, delta x. Let's divide both sides by delta x. So divide both sides by delta x. So I'm going to do a delta x down here and a delta x over here. This one cancels. Here, this one cancels. This term gets divided by a delta x. This term here gets divided by a delta x. This delta x canceled because we divided both sides by delta x. Oh yeah, I know, you can feel it and you're like, wait, this is that math trickery about to happen again. How did they, what? This trick. Now we take the limit on both sides, set delta x to 0. And yes, we get a derivative, a partial derivative of the tangent function with respect to theta. Now hold on, don't take the partial. Here, the tangent, we can interpret that as a derivative. So in 1 second here, I'll show you, we can interpret the tangent as a derivative. And now we'll have a second partial with respect to t on the left side and a second partial with respect to x on the right side. So now finally here, so when you send delta x to 0, when we do this limit on both sides, that's where this partial comes from, right? This thing becomes a derivative, right? So that's where this partial comes from when we send delta x to 0. So now finally here, one last piece is I claim that the slope of the string is actually represented by tangent theta. Because this was the string and theta was that angle between the horizon and how much the string was deflecting. So it was basically tangent of theta, as you remember, if you look at the little triangle, is rise over run. It's delta y over delta x, but rise over run, that's our definition of slope. And here, as you know from calculus, the slope is the first derivative with respect to x. So tangent theta, I replace here, it's a partial derivative with respect to x. So yeah, take that, magic and trickery. I replace the tangent theta with a partial, and now I've got a partial with respect to u on the other side. And so if you go back to the original equation here, so now I'm going to replace this term right here, this whole thing gets replaced. So here it is. And so here we go. A wave equation is born. Yay. So we can divide both sides by the density and write it in this form. So here you will eventually just write this as some constant, and for our purely theoretical purposes, we'll assume there's no gravity. And so, then we get our full-on wave equation. So here let g equal 0, assume the density is constant, and just replace this expression here. We're going to call it c squared. Why do we call it c squared? Because if you actually calculate what it is, it should be a non-negative constant. So unlike, I guess even in the heat equation, it had to be non-negative. Yeah, so here we're just making c squared. I think when we do some other analysis of it, c, the square root of this term, turns out to be a speed. And so I think they're calling it c squared because eventually in the analysis, when we study we'll be interested in looking at the square root of this thing. Okay, so I'll come back to why we're using c squared specifically. It's because later we're going to take a square root, and this will turn out to be a wave speed, so I don't want to get too ahead of myself here because it won't make sense otherwise without the proper explanation. But yeah, so here, just for now, let's accept that it's c squared. Okay, and so now we get our one-dimensional wave equation. And so we should immediately compare it to the heat equation. So the heat equation was partial u, partial t. And so with the heat equation, we didn't have, so here it's the second partial with respect to t, right? So partial u, partial t, that's supposed to be a u. I'll try that again. So partial u, partial t equals, then we've got the old k, and then we've got, it's similar, we've got a second partial with respect to x. So let's just compare and contrast heat equation and wave equation. Evan.
Yeah, I had a question. So that T0 term, that is our constant force of tension throughout the string.
Yeah, right. That horizontal tensile force. Yeah.
Because earlier we treated it as a function. So basically we treated it as a function so we could take the derivative of it. But then after we did that, we just treated it like a constant term. We're
treating the horizontal component of the tension as a function, but the vertical component we're treating as a function, as
okay.
Constant.
So T naught is the horizontal tension, right? Okay, got it.
Right. So if you had a guitar and you turned the key on the end of the guitar, that would increase the tension, I believe. So I think that's what's going on with, that's that horizontal tension. So folks, Do you remember when we solved the heat equation? Oh, okay, so 5 minutes, okay, good. So you remember when we solved the heat equation, where did the decaying exponential time term come from? When we did separation of variables, because this is a single t derivative, we got this equation like g prime equals, lambda g. And because of that, you did g prime over g, and the integral of g prime over g is ln, and then you exponentiate it, right? There's probably a t in here somewhere. I don't know. Okay, I don't know. Yeah. Okay. So now we have a second derivative. Just like on the other side, think about in our heat equation, what happens because of the second derivative here in our separation of variables? You get f double prime equals lambda f. And then this gives us a wave. Yes, this leads to the cosine sine business. True? So can you predict here? Because I have a second derivative with respect to t and a second derivative with respect to x. When we do separation of variables, this will give me a second order ODE, which will give me cosine and sine terms in the x variable. This is second order in t. This will give me cosine and sine terms in the t variable. And we talked about a space and time wave when the string vibrates up and down. So mathematically, it's starting to look like that's what's going to happen. But that to me is kind of scary because the exponential time decaying term in the heat equation was awesome for convergence. Now, if you're telling me the function in the x and t variable are both oscillating trig functions, what does that do to our convergence behavior? That's right. I'm ruining your sleep for tonight. Ha ha. So, all right, folks, I'm going to wrap up the discussion of the wave equation model. And on Monday, we'll talk about some physical properties. And then on Wednesday, we'll start solving it. And of course, none of this stuff will be on the test next week. So, don't worry for that. But it'll be like a good review in the sense that we're going to do separation of variables again. You know what I mean? So in that sense, it'll be a good review. So here's our wave equation. The second derivative with respect to t, think of that as the vertical acceleration. This term is thought of as a restoring force due to tension. I mean, and that's something you'll have to think about. It's not really a force. It's probably a force after you multiply it by area or something, mass or something. They've canceled some constant terms. Here you have gravity. It's not a force, right? We need force mass times acceleration. So here we've canceled a mass term or something. So G is our gravity. And then we have a potential external force, like due to a guitar pick or a violin bow. An initial position. So think about, for the rod, we had an initial temperature. Now when t equals 0, that's the initial position of the string. If no one's messing with the string and you just tie the string and walk away, then the initial position will be that trivial position, trivial equilibrium. Otherwise, we could do an initial position where we say, okay, let me slightly pull the string up in the middle, for example. Let me slightly pull it up, and now that'll be my, and then let me wait a couple of seconds, and that'll be my start position, and then I'm going to let it go. And so ux of 0 would be this shape. If you graph that with x on the x-axis and u on the y-axis, that'd give you the shape of the string from 0 to L. It's initial displacement, depending, what you're doing with it. And then we have our initial velocity. So think about this. This is really subtle. You could either, pull the string up, wait a second, and then let it go, or from below, like with a guitar pick or your nail, you could just, swing your arm up and strike the string, thereby giving it an initial position, deforming its shape, but also imparting it with an initial velocity. and you strike the string, so it goes flying up with initial velocity, and then that starts the dynamic motion. As opposed to, let me take the string, pull it up, and then wait for a second, and then just let it go. And I haven't added any force to it, any initial velocity to it. So here, the partial of u with respect to t at t equal to 0. So here, remember, please keep in mind here, we're replacing the t variables. And then we have our boundary conditions where we're replacing the x variables. So with the boundary conditions, we say the ends are tied. That is, there's no, the vertical position is fixed at that trivial equilibrium 0 position. So now we have PDE, boundary condition, and initial conditions. We have a full problem. So here's some variations that I guess I can talk about next time. And it's about whether you have transverse motion, whether you have stiffness and resistance to bending. In this case, you incorporate Young's modulus, and here R incorporates the thickness of the string. Here you have damped motion, where you're plucking the string, and maybe you've got a finger on the string, and it's damping the motion. So there's a damped motion term here. And then for a drum, if you had a 2D membrane, this would be sort of the 2D version of the simple wave equation. And if you have, so this is a model for if you have motion in the horizontal direction, in the longitudinal vibrations. Okay, and here, so we're using V here. This is actually a different type of model, and I'll talk about that a little bit next time, but we're going to mainly focus on just kind of the simple 1D wave equation model. We'll also talk about the equation with damping. Okay. All right, folks, that's my time. I thank you for your patience. We've started the wave equation, so we'll talk about the physical ramifications, and then we'll just do separation of variables, just like with heat equation. Okay. All right, thank you, everybody. Have a great weekend. Be safe, and I'm going to stop right here.